Hello, everyone. It's me, Billy Younger, again from www.youtube.com/physics, or excuse me, /Billy Younger Physics Solutions, with the B in Billy, the Y in Younger, the capital P in physics, and then the first S in solutions, all capitalized. You'll see that when I actually turn on my iPad. But anyways, I'm here to solve yet another physics problem, and this one's a little less typical. This isn't one where they're making use of a specific equation they gave you. They're making use of the fact that you have had, for instance, high school algebra 1 or high school algebra 2, specifically with conditions like the variable y is directly related to the variable x. That often means y is equal to some constant times x, or the variable y is directly related to the square of x, in which case the y is equal to some constant times the square of x, and so on and so forth. So we're going to make use of a problem like that, and it's going to be a more, let's say, realistic type problem, something that I've actually used myself to sort of make sense of whether it's reasonable for me to speed sometimes or not. So let's start off by sharing the screen so that you can actually read the problem. So here's the problem. You assume that at a higher speed, your car's fuel efficiency, which I'm given the symbol epsilon, which is measured in miles per gallon, is inversely related to the square of the car's average velocity. And further, you assume that at 62.0 miles per hour, which we're often just going to call MPH, your fuel efficiency is 38.40 miles per gallon. So we have a car at high speed. It appears that the fuel efficiency is inversely proportional to the square of the speed. Obviously, that means efficiency is equal to some constant divided by velocity squared. Now the question says, running late for work one day, you decide to speed an average 77.0 miles per hour, well over the speed limit on your 50.0 mile trip to work. A, how much time did you save compared to averaging 62.0 miles per hour? So we're trying to figure out how much time did I save if the trip really is 50 miles and I average 77 miles per hour instead of 62 miles per hour. Part B, how much more gas did you use? In other words, we're going to make use of our idea of what fuel efficiency depends on and see what the fuel efficiency was in the case where I average 62 miles per hour versus the case where I average 77 miles per hour. And then I'm going to see what the difference in the number of gallons is. And then finally, in C, if you did this 100 times per year, how much total gas would you use? How much total time would you save? And if gas costs $3.19 per gallon, how much did the extra gas, or excuse me, how much did the extra gas cost you? I wrote save you for some reason. I have no idea why I did that. And how much did it cost per hour? So in other words, what we're trying to see is how does that compare, for instance, to a typical average wage? If for instance, you find that the gas cost is obviously going to be higher, does it make up for the number of hours you work? So like if you make, let's say you make $15 an hour and it costs you $15 for each of those trips, and you only saved 1 hour, then you came on pat. Basically, it was even. So that's really what the problem's about. What I'm going to do now is I'm going to take my document, which would normally be your piece of paper, of course, and I'm going to write down the key values. What I know is the key values are the efficiency in miles per gallon is equal to 38.40, and that's MPG, and that's only at again the average speed equal to 62.0, and again I'm going to write MPH instead of miles over gallons. The trip to work length work is going to be 50.0 miles. Again, I'm using traditional statutory slash British units, just because that's normally what comes at us when we're talking about our car. One day we're going to run 77 miles per hour instead of the normal 50 or 62. So in part A, they want to know time saved. So I'll write T saved equals question mark for S average equals, in this case, it was 77.0 mph. Part B, it says how much more gas did you use? So delta gas, which I'll call delta V gas, and in this case I mean V for gallons of gas, is equal to question mark, and I'll say in gallons just to remind us that that is V for volume. And then C, at 100 times per year, delta V gas per year equals question mark. Let's say the cost per year is equal to question mark. That's the second part of part C. And then they say if let's say if the, I'll call it expense, I'll say a lowercase e of gas is equal to $3.199 per gallon, then delta E per year equals question mark. And not only that, I will say delta E per hour equals question mark. So those are the symbols as I read them off to you. Now I'm going to stop sharing the screen there and show you what I actually wrote. I'm going to now share screen with my iPad. And you can see what I wrote down. I wrote the fuel efficiency is 38.40 miles per gallon. Notice I just used the symbol that the problem gave me. I said that's at an average speed of 62.0 miles per hour. I wrote down that L, the distance to work, was 50.0 miles. In part A, I was asked how much time was saved by going 77.0 miles per hour. In part B, I asked how much extra gas was used. In other words, the delta volume of the gas in gallons. And then in part C, I'm going to assume that I did that 50-mile trip 100 times per year and figure out how much gas I used. And specifically, if you did this 100 times per year, how much total extra gas would you use? How much total time would you save? That's another question we're looking at. And I think I didn't write that down. Yes. T total per year equals question mark. As how much total time would you save? And part the last part was if gas costs $3.19 a gallon, how much extra gas, how much did the extra gas cost you, and how much is that in dollars per hour? So let's go ahead and get started with solving this problem. I will use, let's say, a nice dark green for my solution. So I'm going to say solution. I'm going to start with part A, and part A is just asking how much time did you save compared to 62 miles per hour. So we know that S average is equal to distance traveled divided by time taken. If I just plug the numbers in, which I normally don't like to do, I like to solve for the variable first and then plug the numbers in. What I want to do is see how long it takes for me at 62 miles per hour, and then see how long it takes for me at 77 miles per hour, and then subtract them. So I can put in, for instance, 62.0 mph, which remember is miles divided by hours, is equal to 50.0 miles over t. So solving for t, all I have to do is divide 50 by 62, divided by 62.0 mph, and I'll get t is t, and I'll say t at 62 just to remind us. So t at 62 should be 0.806 hours, and I believe that's what that's what I got previously when I did this calculation, so that gives me some confidence. 0.80. Notice I'm using 3 sig figs in both, so I'll call that 0.806. I always carry one extra digit. That extra digit in this case actually rounds to 5. So to make sure there's no ambiguity, I'll put down 2 extra digits, 4, 5, and that is hours. And obviously, if you multiply that by 60, that would give you the total time in minutes, which might be more meaningful to you, but we're just needing it for hours. Now I want to see what the time is at 77 miles per hour. We already seen how the math works out, so I can say t at 77.0 is going to equal 50.0 miles divided by 77.0 mph. And in this case, I'm going to say 50 divided by 77, and this gives me 0. And I did say 77, right? Yeah, 50 divided by 77, and I get 0.649. Again, 3 sig figs with 3 sig figs, so 649. And in this case, the next digit is 3 and then 5. So the 3 rounds to 4. I'll just put the 4 here, and that's hours. So now I have that. Exactly how much time I saved is, and I'm again checking that 77 because it seems the previous calculation I actually got a different answer for 50 divided by 77. So I'm going to now say time saved for part A is equal to 0.80645 hours minus 0.6494 hours. Notice I've got different number of sig figs on there, so that's kind of odd. But I'll say minus, and I get 0.157. And the next digit is actually 0 and then 9. So the extra sig fig is just going to round to 1. So I save about 0.1571 hours. If I multiply that by 60, just to give you a ballpark figure, saving about 9 minutes. So that might actually be worthwhile. But anyways, we'll worry about that later. So I now have 0.1571 hours saved. I'm going to box that off in red because that is the actual answer to the question. The question said, how much time did you save compared to averaging 62 miles per hour? Now part B is how much more gas did you use? So for part B, I want to calculate the fuel efficiency. What I know is efficiency is equal to some constant, which I'll just call K, over, in this case, the velocity. Actually, let me do speed since I'm sticking with speed right now, over the speed squared. And I know that, in fact, 38.40 miles per gallon is what you get when you take K and divide it by 62.0 mph squared. So that K turns out to be 38.40 mpg times 62.0 mph squared. Sorry that got so tight there, but that gets me ultimately my K. So I'm going to take 38.40 and I'll multiply it by 62 squared. And that's going to give me roughly 147,609.6. And notice the units turn out to be miles squared, miles cubed. And then per gallon hour squared. That's really what the units are. Obviously, I use 4 sig figs and 3 sig figs. So to be honest with you, all of these digits, the 6, 0, 9, and the 6 are all extra sig figs. They're not really sig figs at all. So with that in mind, what I want to do is see what the fuel efficiency is at 77 using that K, and then find the difference in the amount of fuel I use in the two cases. So this implies that efficiency at 77 is equal to that same number, 147, comma, let's say 610. That's more than enough extra sig figs, obviously. That turns out to be miles cubed per gallon hour squared, and all that's going to be divided by 77.0 mph squared. So if I divide that by parentheses 77, notice I said parentheses because if I do 77 and then do quantity squared, it should only apply to the 77, but you always want to worry about that in terms of order of operations. So when I divide that 147,610 by 77 squared, I should actually just get back 3 sig figs. That's going to be 24.96. And if I try to round that to 3 sig figs, that's going to be 24.9 with 1 extra sig fig of 0. So let's call that 24.90 miles per gallon. So instead of the 38.4 miles per gallon that I got at 62, now I'm getting 24.9 miles per gallon. So let's see how many gallons I use. So gallons, or excuse me, we ended up using the symbol V. So I'll use the symbol V. So I'll say V at 62. Of course, you have the volume of the gas is basically just the number of miles divided by miles per gallon, because when you divide miles by miles per gallon, you end up taking the miles and multiplying it by the reciprocal of the unit, which is gallons per mile. So miles times gallons per mile just gives you gallons. So I'm going to say, in fact, 62 or 50 miles divided by 38.40 miles per gallon. And that gives me 1.302 gallons. Now, that's carrying 1 extra sig fig. When I do the V at 77, I'm going to get 50.0 miles divided by in this case, 24.90 miles per gallon. And in that case, I get 2.008, carrying one extra sig fig again, and that's gallons. So it turns out my delta V, which is what I was looking for, delta V gas, is actually equal to 2.008 gallons minus 1.302 gallons. And that gives me 0.7060 with it one extra sig fig gallons. So in terms of extra gas it cost me, let me write it this way. I'll say equals delta V gas. And I'll box it off in red because that is one of my final answers. So I now know that it cost me an extra 0.7 of a gallon, obviously. So that's kind of helpful. That was part B. How much more gas did you use? Now, finally, when we get to part C, I'll need to flip to the next page. I don't want to try to fit it in there, but it says if you did this 100 times per year, how much total extra gas would you use? So in other words, I'm going to just take this number and multiply it by 100, and that'd be the extra gas I'd use. You could basically consider that maybe you did it to and from work on 50 different days over the whole year, and that would be somewhat reasonable. It says, so how much extra gas would you use if you did it 100 times? How much total time would you save? So we're going to take that time that we saved, the 0.1571 hours, we're going to multiply that by 100 as well. And then we're going to say if the gas costs $3.19 per gallon, I'm going to multiply that times the new gallons after 100. So my figures that I need are 0.1571 hours and 0.706 gallons. 0.1571 hours, and the other figure was 0.7060, 0.7060 gallons, and this is T saved, and that's per trip, and this is delta V gas per trip. So in part C, what we want to do is we want to figure out, first off, I did this 100 times per year, how much gas would I use? So per year implies multiply by 100. So delta V gas per year equals 100 times per year multiplied by, again, we're just talking about the extra gas right now. So this would be 0.7060 gallons. And that gives me delta V gas per year. Notice I'm writing it slightly different, equal to 70.60 gallons per year. So that's one answer. The next part is how much total time would you save? So T, like using green, sorry, T saved per year is equal to 100 times that we do it per year. I multiply that by 0.1571 hours. And you can see that the math works out quite nicely to 15.71 hours per year. So T saved per year is really equal to about 15.71 with one extra digit hours per year. And I want to box that out for red because that's yet another answer that we needed. Now it says if gas costs 3.199 per gallon, how much did the extra gas cost you? So what I called that before was the expense E for gas. So E, oops, there you go again, my red. E gas per year is equal to basically the $3.199 per gallon times the 70.60, extra digit there, of course, gallons per year. And that gives me times 3.199. That gives me 225 point, let's say $86 per year. Okay, now I had 3 sig figs for the 70.6 and I had 4 for the other. So really both of this 8 and the 6 are extra digits. They're not sig figs, so I really should technically be calling this $226, but by underlining it, I've let everybody know that. So that's how much the extra gas costs you. So I'm going to go ahead and write that as extra gas. All right, excuse me, expensive gas per year for speeding, and that's just above what you'd normally be paying. I'm going to call that 225.86. Again, reminding everybody that the sig figs stop at the ones place. I'll box this off. Now here's the neat part. It says how much did it cost you per hour? So this is where you can really see, was it worth it from a fiduciary standpoint? So how much did it cost per hour? I think before, what did I call that? Delta E per hour. So I'm going to say delta E, again with the stupid red. I'm going to say delta E per hour. So what we discovered was over that year, the cost was $225.86. Again, we should round that to 226 as far as significant figures go. But the only amount of time that it saved us was 15.71 hours. So I'm going to put 15.71 hours there. And again, you see the 15.71, the 1 is insignificant. So we really have 3 sig figs in both cases. So I'm going to take this 225.86. I'm going to divide it by 15.71. And that gives me, in fact, 14.38, carrying 1 extra sig figure, dollars per hour. So that tells us basically that unless we're making $14.38 per hour, we're actually costing more to speed than we are not to. Of course, that doesn't take into account neat little things like time clocks often only work on 15 or 7.5 minute intervals and stuff like that. So if you only are 7 minutes late, you're probably still counted as being on time, stuff like that. But the ultimate result was delta expense for gas per hour turned out to be $14.38, and I'll box that off. So that's basically it. So again, this is not a typical physics problem that they ask you, but occasionally a physics problem like that does pop up, and the reason why is because in the mind of the physics teacher and in the mind of physics textbook authors, we go on the assumption that you sort of have mastered all those courses before your physics course. In other words, if you're taking like this course I'm teaching right now this semester, I'm teaching 2 calculus-based physics courses. So they're assuming that I went through the typical high school scenario, which was I did basic arithmetic for years, learning how to do long division, multiplication by hand, and then of course using calculators and adding, subtracting, knowing the multiplication facts. But then after that, I went into pre-algebra, where I learned how to deal with positive and negative numbers, both multiplication and division. I started to learn the basics of how to solve simple equations. And then I took, of course, Algebra 1, where we were introduced to something like directly related and inversely related, are proportional versus inversely proportional, stuff like that. That would have been a very typical Algebra 1/Algebra 2. Y equals mx plus b is an expression they'd expect us to understand and know how to work out for a given set of data. You should be able to find what the actual graph of y versus x is if it's linear related. Then by the time you get to Algebra 2, they expect, being able to divide polynomials, being able to factor really well, as well as in Algebra 1. They expect you to have had geometry, so that that vertical angles are congruent, or that if you take 2 parallel lines and put another another line across that line, alternate interior angles are equal, corresponding angles are equal, stuff like that. So they really do expect you to have mastered all that stuff, as well as all the stuff you learned in pre-calculus and calculus. So don't be surprised if they ask you something that you haven't heard of since middle school. That's a very real possibility. So I hope this particular problem helps you. I like it. It's actually a realistic problem. It gives you some realistic numbers to think about, and maybe it'll keep you safer for not speeding, because it really doesn't. It takes a huge difference in your speed to make any kind of difference in your time, and a huge difference in speed makes a huge difference in the fuel efficiency. So have a good day. Thank you for checking this out.